Good afternoon. So let us begin today's lecture. It's about identification of grand-design and flocculent spiral galaxies using convolutional neural network. So let me explain what it all means. Okay, yeah. So this is roughly the plan of my talk. So we will begin with a brief overview of what galactic spiral arms are, because based on galactic spiral arms, we classify galaxies as either grand design galaxies, that is, galaxies having grand designed spiral arms, or flocculent galaxies, that means galaxies, firstly, they have to be spiral galaxies, that is, galaxies showing spiral arms. So I hope by now you know that all galaxies are not disk galaxies, and even if it is a disk galaxy, it may or may not have a spiral arm or spiral arms, right? Depending on its position on the Hubble's tuning fork, right? On the handle side of the tuning fork, you have the RD types or the elliptical galaxies. As the name suggests, the morphology is elliptical. On the forked side of the tuning fork, you have two forks, right? You have the spiral galaxies, and at the junction, you have the S0 galaxies. So they are very peculiar. They share characteristics between the spirals. Their characteristics are between those of spirals and those of ellipticals, right? So S0 galaxies or lenticular galaxies, their appearance is mostly of that of elliptical galaxies, like a lens, but they're devoid of spiral arms, but their kinematics is more like disk galaxies. That is, they are rotation supported. So as you know, disk galaxies are rotation supported, and elliptical galaxies are uh, supported by random motion, mostly. We can say that. Okay. So when I talk of spiral galaxies, we have these galaxies on the forked end of the tuning fork, Hubble's tuning fork, right? And they are characterized by magnificent spiral arms. Okay, so we will begin with a brief overview of what galactic spiral arms are. Uh, uh, what are the theories which have been proposed to understand the existence of those spiral arms? And then we'll end with the motivation or the open questions which could still not be addressed in this area of research, which will form the basis or motivation of the work which we have done, which I'll come to in the third part of the talk, as you have seen. But after that, you know, after giving you a background of what galactic spiral arms are, I'll move on to a brief description of what convolutional neural networks are. Okay. So this is the tool, the machine learning tool, which we have used to classify this spiral galaxies. Okay. So, so what does that mean? Uh, does that mean that, as of now, galactic like spiral galaxies were not classified into flocculents and grand designs? No. I mean, as I already said, already maybe starting from 1960s or even before that, people had seen these variations or different types of spiral arms in the spiral galaxies, and they also proposed theories to explain those existence of those spiral arms. But as you know, this is the era of big data, and you may have already guessed. How do you distinguish between a spiral galaxy which has a flocculent nature and a spiral galaxy which a grand designed nature by visual inspection? We will soon see what do I mean by a grand design galaxy and a flocculent. They are spiral galaxies, but they are very different in appearance. Okay, so all this while, since the number of observations of galaxies were limited, people used to classify them visually. Just take the optical image of the galaxy or the IR image of the galaxy. Looking at the image, you can classify. But as you know, I mean, we are now in the era of big data, and manual classification or classification by human intervention or visual classification whatever you would like to say, has limited scope. I mean, we cannot actually do justice to the huge amount of data which the next generation of telescopes would accumulate merely by human intervention or visual inspection. We do have to, it's imperative we take the help of the machines to do that. Why? I mean, are we not more efficient than the machines or anything like that? It's nothing like that. It's just the speed, right? I mean, if we will see how much the speed improves if we take the help of machines as compared to human intervention. For example, in this task of classification of galaxy images, it can be done in seconds, actually, thousands of galaxies. I mean, that much we can appreciate, right? Even if we don't know about what galactic spiral arms are, what Grand-designs are, what flocculants are, no one can classify images. Suppose I ask you I give you a mixture of, red cards and yellow cards, and I ask you that you segregate them into two heaps. Can you do that in few seconds? None of us can do that, right? So it is similar to that, right? Classification of images, but machines can do that in a matter of seconds. So, I mean, that is the main motivation, speed. Okay? For employing these machine learning techniques for classification of these spiral galaxies. Now you can employ this technique for any purpose, for classification of any image, right? I mean, as you will see, convolutional neural networks are mainly meant for image classification. Okay. So anyway, let's come back to the plan of the talk. We'll start with an overview what convolutional neural networks are, and then I will give you a very simplistic model, a very simplistic model to understand what how these neural networks work. Then we'll talk about the optimization problem. It's, at the end of the day, a trial and error. I mean, you are teaching the model or the neural network how to classify some kind of images. In our case, it is galactic spiral arms. It can be any kind of images. It can be, some images of me and some images of you, or any one of you. We can train, if we have enough number. I mean, thanks to our mobile phones, we have, at least few hundred images, at least even at this point of time in our mobile phones. Huh? If you give me 300 images of yourself, and if I have 300 images, for example, it should be of the order of 100. Okay. I mean, we can train one convolutional neural network so that, if I give it new images later, new images of me or new images of you, it will tell you which is me and which is you. And I mean, it's nothing of a wonder, right? We see this kind of things daily. Even Google, even in Gmail, uh, they have this tagging procedure. I think they let you know. I mean, they find out some images and then they suggest names. I mean, is it you or is it your friend, right? So it's being, I mean, it's there for quite some time now, and unknowingly or knowingly, we are also part of it, and we are also using it in various appliances we handle in our day-to-day life. But maybe today we will look at a more, formal look at the tool which has been the basis of all this uh, apps or whatever we use these days. Okay, so it's basically you are training the model, and it is trained by a trial and error technique. Okay, there is a type over here. It is optimization problem. Okay, and the optimization which is used, for example, list square fitting, when you fit a straight line to a bunch of points. Okay, that is also a trial and error technique, right? So there also you employ some kind of algorithm, the LM algorithm, and so on. Similarly, for our the training of our neural network by trial and error method, there is a technique, and it is called the gradient descent method, which we will see. And then at the end of the day, we have to judge, right, whose network is better. Suppose develop a convolutional neural network to classify some images, and you also develop another convolutional neural network to classify the same kind of images. Whose is better? So that will be decided by the network performance diagnostics. Okay. So with these two things in place, galactic spiral arms, which are the types of images which we are going to classify, and the tool, the convolutional neural network. I'll quickly give you a new piece of work, research, which we have recently done, uh, and to develop a neural network which will classify this flocculent and Grand-design type of galactic spiral arms. And using that neural network, we have actually done new classifications of about 1500 new galaxies. Okay, so we'll wind up the talk with that and the summary. Okay, so let's begin the first part. Okay, so about 30% of all massive galaxies are spiral galaxies. So when I say spiral, I mean these arms. I hope you can see my cursor. Okay, one of you can please respond.
Yeah, we
Hello?
can see. We can see.
Yes, we can.
Achha, these are the spiral arms. Okay. This is also a spiral galaxy. Maybe we are not uh, familiar with this kind of spiral features, but this is also a spiral galaxy. Okay. Right. So this one is known as a grand design spiral galaxy. It's just a nomenclature. Okay. These are the flocculent spiral galaxy. Flocculent means just feathery appearance. Okay. And again, at this point of time, it might appear to you this one is equally feathery or flocculent compared to this, but definitely there is a difference, right? This one is feathery, but it has two distinct arms, which is lacking over here, right? So this is a very interesting scenario again to drive home the point. If I show you only one picture of a grand design and one picture of a flocculent, it's very difficult to teach you, right? Which is a grand design and which is a flocculent. On the other hand, if I give you a few hundred grand designs and few hundred flocculents, right? I mean, you will definitely make out. You will teach yourself. I don't have to say, there is a spiral, distinct spiral arms being visible in the grand design case. Nothing of that sort is visible. I need not have told you all this. You could have identified that by yourself, right? So that is the magic of biological neural networks. So anyway, we will see how artificial neural networks get trained the same way. Okay, anyway, that was just an aside. So spiral galaxies are ubiquitous. When we are doing a study of any entity, of an astronomical entity, it has to be substantial in number or in ubiquitous to be important for a study. Then why are, as far as galactic dynamics or galaxy formation and evolution is concerned, why are they important? See, these are non-axisymmetric features. I mean, that is very evident from the pictures. And non-axisymmetric features will help in angular momentum transport. As you know that these galaxies are fundamentally angular momentum supported, right? Which is which is responsible for their disky appearance also. And as you know, I mean, you can also work it out. It is a fun problem. If you had a spherically symmetric entity, a spherically symmetric disk within a spherically symmetric dark matter halo, there wouldn't be any angular momentum transport between the disk and the dark matter halo. Okay, you can work this out. This is a fun problem in classical mechanics. So there has to be some sort of a non-axisymmetry present in the disk, okay, for a angular momentum transport. Even if you had a disk, circularly symmetric, like our normally the galactic disk is taken to be circularly symmetric, right? In a spherical dark matter, even then there won't be any angular momentum transport. You will have to have a quadruple moment in the potential for an angular momentum transport, and this non-axisymmetry is the very thing which is responsible for the presence of a quadruple moment in the gravitational potential of the galaxy. Okay, just a few technical terms if you are interested. Finally, Why do these spiral arms look magnificent and brilliant? Because these are the sites of primary sites of star formation in these galaxies. Okay, so last but not the least, they are the primary sites of star formation in the galaxies, and hence they are important. The spiral arms. Okay. Now, there should be some quantitative features. I mean, there should be some properties of the spiral arms which we can quantify. We'll see. I mean, in order to understand the dynamics, we have to quantify the kinematics, right? So, what are those characteristics? Firstly, let us understand what is a leading or what is a trailing spiral arm. A leading spiral arm is one which is the direction of the spiral is in the direction of the rotation of the galaxy. So if you see here, the rotation of the sense of rotation of the galaxy is indicated. It is anti-clockwise. And here, this spiral arm has the same sense, the curvature is in the same sense as the rotation of the galaxy, right? So this is a leading spiral arm. When the curvature of the spiral arm is in the direction of the rotation of the galaxy, it is called a leading spiral arm. So the left one is a leading spiral. This one, on the other hand, its sense of curvature is opposite to the sense of rotation of the galaxy, right? It is called a trailing spiral arm. Okay. So also these spiral arms, when we see the image of a spiral galaxy, we see a magnificent spiral arm, right? But it is not evident, it is not, I mean, clear to us that actually these spiral arms are slowly rotating. But as you know, in astronomy, it takes like giga years, the time scale of one dynamical time scale to complete one rotation about the center of the galaxy. So definitely we don't see that the spiral arm is rotating, but actually they are rotating, and indirectly we can figure that out. Okay, so it is not only a pattern like this, stationary pattern on the galaxy is rotating. Along with that, this one is also rotating, but there is a difference. Okay, so as I said, this is the direction of the rotation of the galaxy, and this is the direction of rotation of the spiral arm. There is a major difference between the rotation of the galaxy and the rotation of the spiral arm. So as you know, you probably know by now that the galaxy is in differential rotation, right? That means the galaxy doesn't have a fixed angular velocity at all radii, right? As you know, the angular velocity is fixed maybe within the inner radii for a few kpc or so. After that, it falls off with radius. So mostly over the disk of the galaxy, the angular velocity is not fixed. That means the disk does not undergo solid body rotation. So when you rotate a ball, right, it is a ball is a solid. So irrespective of the distance of the point from the axis of the rotation of the ball, right? It has the same angular velocity. It does not have the same linear velocity. Linear velocity is angular velocity into radius, right? That is the reason your linear velocity at the poles is 0, right? The linear velocity is maximum at the equator. If our Earth is also a solid body, it is undergoing solid body rotation. Unlike that, our galaxy is undergoing differential rotation, and that is evident from the rotation curve, right? If the linear velocity becomes constant after a certain radius, that means the angular velocity is falling off with radius. Okay, but the spiral arm, from indirect means we have established that the spiral arm is, moves as a whole. It is undergoing solid body rotation. So you can, visualize, you can compare this situation with the something like a ceiling fan. You have a differentially rotating disk, but on the top of that, you fix a ceiling fan. The ceiling fan is rather, sleek and it has only two arms. Whether it would be useful for in the summer, I mean, that's a different question. But it is moving as a whole. It has a constant angular velocity, and which is known as the pattern speed of the spiral arm. Okay, that is very different from the rotational speed of the galactic disk. Okay, which is undergoing differential rotation. So in this case, the pattern is moving in the direction of the movement of the galaxy, rotation of the galaxy. But in the case of the trailing spiral arm, it is moving opposite to the direction of rotation of the galaxy. Okay. So this is one important aspect which we should keep in mind. The other important aspect is the pitch angle. So what is the pitch angle? The pitch angle is a metric to understand how tightly wound or how loosely wound a spiral arm is. Okay. So the pitch angle is this angle. Suppose at any radius r, you want to find out what is the pitch angle of the spiral arm. So there, at that radius, you have to construct an imaginary circle of radius r. Okay. And this is the perpendicular. I mean, this is the radius. And you draw a tangent to that radius. And this angle, psi, denoted by psi, is the pitch angle. Right? So if your arm is very tightly wound, you will have a small value of pitch angle. Very tightly wound is almost, circular, right? So your pitch angle would be almost 0. If you have a loosely wound spiral arm, like the, data type galaxies like SC and SD, your pitch angle would be larger. Okay, fine. Right. Now, as I was telling you that this spiral pattern moves with a pattern speed. Now, what it is it just a material arm, as I was telling you, like a ceiling fan, which is part of the, I mean, I just told you it's like a ceiling fan, imagine a ceiling fan moving over and above the differential rotating disk. So people actually arrived at this picture much later. So initially it was supposed it was part of the disk itself. Okay. But there was a serious problem to that. What is that problem? It is called the winding problem of the material arm. What is the winding problem? So let us understand this. Suppose I have a differentially rotating disk, which is my galactic disk here, and as I move outward, my angular speed falls off with radius, right? So this annulus rotates at a slower speed compared to this annulus. Okay. So what happens if I suppose I can afford to draw on the surface of the galaxy a spiral pattern like this. Okay, with chalk, I just draw a pattern like this. What would happen? After some time, if you look at that, those bunch of points which had constituted the spiral at t equal to 0, for example, this would become like this, right? Just because your different annuli are not being at the same angular speed. Right? For example, this would not happen if you draw a spiral pattern on the surface of a solid ball, a cricket ball. It would not happen. And then you spin it. Will the pattern get sheared off? I mean, will the pattern, for example, change its shape or appearance after the ball starts spinning? No, right? That is because the ball is spinning like a solid body. It has a constant angular velocity at all radius, at all latitude points. Okay. But here, this is not the case. And as a result, it would get sheared up. So you can imagine, you can do a thought experiment and you will figure out, this is in course of time, this is how the pattern is going to look like. So this is something which you had drawn at t equal to 0. After some time, it will get, wound up like this. And finally, it would get very tightly wound up like this. It very much looks like those mosquito coils, right? So anyway, but in reality, we see, this kind of spiral patterns? No. We do see loosely wound patterns in many galaxies. Okay. So you can argue, maybe it's just a just born state, and eventually, yeah, will get wound up. Who is preventing it to get wound up? Maybe we are just looking at that epoch where it has a slightly, I mean, loosely wounded form. No, I mean, by indirect means, again, from judging the from estimating the uh, for example, the age of the stars and many other indirect diagnostics, we have come to the conclusion it's not a transient. It's mostly in most of the galaxies. I'm not completely ruling out the presence of transient patterns can be there, but in many galaxies, by indirect means, it has been established that this pattern is a long lasting pattern. It is a stationary pattern which is actually moving like a ceiling fan moves, but slowly, superimposed on the motion of the differentially rotating galactic disk. Now, so definitely, if that is the case, okay, if we rule aside the transient spirals, which are also there, but they constitute a minority of the population of spiral galaxies. This is just for your information. You can actually, for this lecture, forget, right? Anyway, I mean, I'm not asking you to forget about that, but I'm saying that they constitute a minority. I'll come back to that again. So galactic disks have differential rotation. So if it had it been a material arm, just a part of the disk, it would have wound up and destroyed the spiral arm in 2 or 3 rotations in dynamics. So what is it? So to understand that, various theories of spiral arm formation has been proposed. Okay. So the first one is the swing amplification theory. Let us not go into the details of this. And then we have the density wave theory. So mainly the swing amplification theory says is used to understand tightly wound spirals like this, right? So if you compare the spiral patterns in these two cases, this is comparatively loosely wound, this is tightly wound, okay, right? So these are nothing. So the understanding is, the theoretical understanding is, these are local non-axisymmetric perturbations in a differentially rotating galactic disk, okay, which are sheared by uh, the differential rotation of the galactic disk to give you a spiral-like appearance. Okay. On the other hand, the density wave theory was proposed to understand the grand design spirals, the long, or in other words, the long lasting spiral. Okay. So in this talk, whenever I say grand design spiral, I would mean a spiral which is stationary, which is long lasting, which are, I mean, which was a matter of concern. I won't say that they are the majority or minority, but which was a matter of concern, the existence of which. Okay. So those are understood as global non-axisymmetric perturbations. Okay, here I have used the word local. See, both are non-axisymmetric. If you have a spiral arm, it has to be a non-axisymmetric perturbation. Okay, when I say, why do I use the word perturbation? I just want to understand. I mean, these were the initial attempts to understand this kind of non-axisymmetric features in the galaxies, right? In the 1960s or so. So always we propose a simplistic model. So, and the simplistic analytical model is, you have a steady state, and you steady state of a symmetric disk, and you just perturb it from the axisymmetric disk by some sort of a non-axisymmetric perturbation. Now, the tightly wound case, uh, we can actually assume a local non-axisymmetric perturbation. Why? Because this is like a periodic boundary condition. Here, it see here it is. If you can see my cursor, there is a density enhancement over here, and then there is a void kind of thing, right? Again, there is a density enhancement void. So it is like harmonically varying about the disk of the galaxy. So if you have a harmonic solution assume, you can propagate it using periodic boundary condition. That is possible if you have a tightly wound kind of spiral. Okay. But if you have a loosely wound kind of a spiral, you cannot do, a periodic, you cannot assume a local non-axisymmetric perturbation. Okay. Because see, it is not as simple as periodically propagating the harmonic solution. So there, your radial dependence comes through the amplitude part, and then you have the harmonic part contains only the azimuthal dependence. Okay. So if you don't get into the depth of all this, no matter, it doesn't matter. Just keep these two things in mind. So these are global non-axisymmetric perturbations, the grand design ones, and these are the local non-axisymmetric perturbations, the tightly wound ones. In this talk, we will consider the model of our flocculent galaxies to be the ones by local non-axisymmetric perturbations. Just this is your take-home message. Okay. Sorry. Right. Now let us look at an interesting thing over here. So I have two pictures. Swing amplification, which is the theory of local non-axisymmetric perturbation, which explains our flocculent spirals, okay, which are tightly wound, patchy kind of spirals. And we have the density wave theory, which is a global non-axisymmetric perturbation, which explains the continuous grand design spirals. Okay. So if you remember, our aim in this talk is to develop a convolutional neural network which will classify spiral galaxies into grand design ones, which are, magnificent, continuous, okay, global patterns, and flocculent spirals, which are tightly wound, patchy spiral arms. And the theory of global continuous, loosely wound spirals are the density wave is the density wave theory, and the other theory which explains the flocculent patchy tightly wound spirals is the swing amplification theory. We are not, it's just an piece of information for you. Don't get bothered about how it happens. Okay, right. Okay. So I just wanted to give you a feel of the density wave theory to understand what it is. Okay. So let us take up this example of our traffic congestion. Okay. On a high road. So that would help us to understand what actually this spiral arm is as far as the density wave theory is concerned. That means which, explains the loosely wound grand clean spiral arms. Okay. Right. Suppose there is a convoy of cars. Okay. What happens if it moves, if this bunch of suppose the prime minister's convoy of cars, there would be a traffic congestion, right? Okay. But this traffic congestion is not stationary. Why? Because that convoy is moving anyway, right? It has a motion, but it is slowly moving for whatever reason. Okay. Maybe, this is some sort of an election campaign and the leader is standing on one of the whatever it is. It is moving slowly so that it can attract the attention of the people on the sides of the road, and it is moving slowly, and there is a bunch of cars and there is a traffic congestion, right? So why there is a traffic congestion? Because the cars, when it is approaching this convoy which is also moving, is slowing down, right? Otherwise cars would move at a very high speed on the highway, right? It is slowing down, and maybe if there is some gap or the other, the car would just, some other car, not the part of the convoy, it would just, bypass that and move faster and go away. Again, there would be a bunch of cards. Okay. Some of the cards would be that part of that convoy, but there would be some cards which are just getting, slowed down because of the constriction posed by the convoy. Again, it is moving, right? But all the cars which were behind the convoy is getting slowed down, and there is a density enhancement of car near that convoy. Again, the cars would just find out some gap or the other, move out. So what I'm trying to say, firstly, this density enhancement is not stationary; it is moving. The minister is not standing at one point on the high road; he's moving, but moving very slowly with his you know mm, accompanists and all. And there are other cars also which are causing the density enhancement. But the interesting part of this feature to notice is the density. It is not the same bunch of cars which is present in the enhanced density region, right? Of course, I mean the minister's cards are there, but there are many other cards which are getting slowed down. Then it is finding some way out and then moving out. Okay, so this is like a density wave, right, which is moving. Hmm. And what is the characteristic of the wave? The wave, the density enhancement is not constituted of the same particles, right? Here, by particles, I mean the cards. Part of it, yeah, of course, it's the minister's envoy or convoy, whatever. Huh? But the others are the slowed down cards, which are like, new cards at every point of time are coming and getting slowed down, causing a density enhancement. Those cards are leaving, and again, a fresh bunch of cards are coming. It's coming. Okay. So this situation is very analogous to what is happening in the galaxy as far as the spiral arms are concerned. Okay, so there is a density enhancement along the spiral arm for whatever reason, and when the orbits of stars, in any way, right? Stars are in orbits around the center of the galaxy. When it is encountering this density enhancement, see the orbits of the stars were calculated for an axisymmetric distribution of the galaxy, right? The galactic disk. Now we have imposed one perturbation, as I said, just to have a simplistic understanding of how what things. I mean, how are things? How is it possible to have a density wave? If you have a density enhancement in the same in the form of a perturbation, the cards would go there, feel this depth of the potential well, get slowed down. Again, it will climb out of the potential well and go out, right? But for the time being, see, in these regions where there is a density enhancement, there would be a slowing down of the cars, right? It's like falling into a bumper, or it's somewhat like it's not a bumper, maybe the opposite of a bumper. It will slow down, and as a result, there will be relatively a larger number of starts over here, like relatively a larger number of cards over here compared to at other regions, and then again it continues in its own speed. Again, it finds a density enhancement, falls into the potential will, climbs up. So there is a disruption in its seamless motion, right? Which is actually responsible for the production of this density wave, right? So it is not the same cards which is constituting this density wave. Then it would have been a material arm and unwound itself in no time. It's just it's something else which is very much analogous to the picture of a traffic congestion. Okay, so this is what we all need to just to have a feel of how galactic spiral arms, the real galactic spiral arms are formed. Of course, there is the flocculent picture, which are not long standing, which is not a density wave, but that is not so interesting as far as the physics point of view. So I just wanted to give you a feel of this physics over here, but this is pertaining to only the grand design spirals, which is half of the story for us today. The other half is the flocculent spirals, the patchy ones, which are just local perturbations shared by the differential rotation of the galactic disk. Okay, so this is to do with the theory. Okay, there are other theories also, manifold theory and stochastic star formation. These are okay. Manifold theory is again, something. If you have a bar-like pattern at the center of the galaxy, this is again a non-axisymmetric entity. It will also have its own quadruple movement, and it will drive spiral. I mean, it will lead to the formation of spiral patterns in the galaxy. This is just the manifold theory. And stochastic star formation is again related to the flocculent spiral arms. I mean, stochastic, as you know, is random, right? So random star formation in those pockets of density enhancements is believed to give you the appearance of those patchy spiral arms, which we understand to be flocculents. Okay. Anyway, just to complete the story, I have added these two. Okay. So this is all we had about the theory. Now, what are the open questions? Why? I mean, we are doing the classifications. Good. I mean, we will get a lot of data. We have someone has to classify. But why? I mean, if everything is known and said, we understand how the spiral arms are formed, how the grand designs are formed. I said it is by the density wave. The flocculents are formed by stochastic star formation or swing amplification of local non-axis symmetric instabilities. Then what is the point of doing more classifications? Just because we have data, we'll just go and classify. Yeah, that's a good idea. I mean, eventually something or the other would come up. But that is not the only motivation. The motivation is manifold. The motivation is, I mean, there are various open questions. I mean, we have just seen the tip of the iceberg. And as I mean, maybe I have not talked so much about the nitty-gritties and the intricacies of the theories involved. It's quite a complex field. Okay. So firstly, let me highlight what are the open questions in these fields. And in order to understand the open questions, we propose models, right? And if we propose models, how to check the validity of the models? We have to have more and more data to test our models. And therein comes the importance of classifying more and more spiral galaxies. Because, I'll just give you a small example. When we develop a model, there would be various contributions, right? I mean, there will be various parameters which would be there in the model. For example, there can be an environmental influence. Okay. So we have to have enough number of observed flocculents and grand designs so that it spans the parameter space well enough so that we can test all our models. Suppose as of now, we have flocculents and grand designs which are pertaining, which are there, which is scanning only a limited portion of all the parameters possible, which can regulate the formation of spirals. Then our models will not be very well tested, right? So, I mean, this is the main motivation. So, anyway, coming back to the open questions. So, having said, having talked about density wave theory and having talked about swing amplification, still, till date, simulations fail to produce a stationary spiral pattern with a constant pattern speed. Okay. I mean, I said that, it's the density wave, single wave mode moving with a constant pattern, then it should have been realizable in simulations, no? I mean, you all have seen normal modes in your classical mechanics course, right? And you know that any motion of the spring mass system can be explained as a superposition of the normal mode motion, right? But the normal mode motion also exists, right? So it is like that. Our uh, grand design spiral is a normal mode motion. Then once in a while, that should also be visible. The right, but never, in how much ever you try in the simulations, you never produce a stationary spiral pattern with a constant speed. So what is going wrong? Secondly, we were talking about the manifold theory, like so the theory predicts there should be a correlation between the properties of bars and the spiral arms. As I said, the bar, the central part of the galaxy, that is also non-axis symmetric. Its potential also has a quadrupole moment. So it's very natural it will drive a spiral wave in the galaxy. If that is the case, then the physical properties of the bars should be correlated with the physical properties of the spiral waves. But mostly we don't see that. Then why? Why? What is the problem? Thirdly, in spite of the same atomic hydrogen gas content, grand designs are lower than flocculants. And finally, we see that most of the low surface brightness galaxies are flocculent, are having flocculent spirals. Why this is so? I mean, the theory doesn't answer this. Okay, so there are, I mean, this is not, the list is not exhaustive. There are many such open questions, and that forms the motivation for us to classify, have more and more galaxies classified so that we can properly test our proposed models. Okay, and that is the reason we thought of developing a neural network. So, what is a convolutional neural network? So, I'm sure you attended, yesterday's talk by Dr. Shilu Abraham. She may have already given you some understanding as to what machine learning is and what convolutional neural networks are. But let me, anyway, go through this very quickly and come to the what we have done in this context. Okay. Okay. So, of course, it is part of AI, artificial intelligence, right? Neural networks, as the name suggests, convolutional neural networks. So, artificial intelligence is something in which we use machines to mimic cognitive functions. Cognitive functions, human beings are capable of cognitive functions, right? So, when we use machines to mimic those cognitive functions, we call this artificial intelligence. Now, okay, sorry, there was one question which I didn't. What does non-axisymmetry mean? Non-axisymmetry means that it is not. It is a function of phi also. It is not only radially. It is the function is not a, the potential is not a function of radius alone. Okay, it is a function of phi also. Sorry. Yeah. Let us come back to neural networks now. Artificial intelligence is that which mimics human cognitive functions. Machine learning is computer algorithms that improve through experience. Okay, so this is very important. It is not programming, all of us in the beginning, I mean, when we start our computer studies, we know programming. Programming is very different from machine learning. See, machine learning learns through experience. So when you teach, for example, when you teach a kid to identify the alphabets, you don't program the kid, right? The kid learns through experience. You show the alphabet A many, many times or write the alphabet A many, many times. Then the kid learns through experience. The same thing happens over here. Now, what is artificial neural network? Artificial neural network are computed systems inspired by biological neural networks. Okay. Feature learning in machine learning. So technique for automatic feature detection. So again, I will give the example of alphabet recognition. So how does the kid know this is A? And when after a few days, suppose initially you had an alphabet book in which all the alphabets were written in red, for example. So next day, if you write the alphabets in green, do you think the kid would not be able to recognize? I mean, will the kid say, no, it is not A, or still the kid will recognize, right? How? So, I mean, something is inside which tells the kid that the feature which I should identify is this shape, it is not the color. And it comes through experience, right? I mean, this is obvious. I mean, all of us that can feel that, right? If I tell you this is S, right? And tomorrow, if I give you a rotated picture of slightly rotated, okay, or maybe let us go back to our A. If I give you a tilted A, even then you can identify it is an A, right? The kid can also identify. I'm sure the kid will be able to identify. How? All this while the kid had seen only a red colored A. The kid had seen only a vertical A. How come, when you tilt it, he or she can still identify? Because of the feature identification. From experience, it has seen this, tilt, rotation, color is not something that matters. What it matters is the shape. But of course, it has to come through experience. If you, as I said in the beginning of my talk, I just give you one image of a flocculant and one image of a Grand-design, you will not be able to tell me if I give you 10 more images now and ask you to segregate. You will not be able to. Because, I mean, you don't make out, right, what are the features which is consistent in all the training images, right? So anyway, that is the feature learning. Now, convolutional neural networks are artificial neural networks which takes an input image, assigns learnable weights and biases to various aspects in the image, and is able to differentiate one from the other. And deep convolutional neural networks are convolutional neural networks with multiple features. Okay. So what is, I mean, I'll just wind this up with this. So if you have a picture, right? So suppose when you learn to draw, okay. Suppose suppose you are drawing the face or you are drawing an apple, right? You just draw the outline first, okay? Then you color and then you give the shade, right? Grossly, it is circular in shape, right? And then you will just, superpose the other variations and fine tune it. So here also, the machine gets trained in the same way. It looks for the gross features first, and then, in layer by layer, it looks for the finer features. Okay, right. And then there is, so this is a kind of supervised network. I have some training images and I give those training images to the machine to get trained. So every time it tries to train itself and then validates with whatever is given. Yeah, this is A, this is B, right? It's already given to. And that way it learns, okay, these are the important features. I should, assign most weightages to this kind of lines, these vertical lines. Color is not an important feature. Angle is not an important feature. Okay. So it assigns weights to the different features based on the instruction. The instruction are nothing but the training images. Okay. Anyways, right. So this is the classic problem of recognition of handwritten digits. This can be done using a convolutional neural network, right? So I'm sure that you have seen this kind of things in yesterday's talk. So this is your input layer. This is your output layer. Okay. These are the hidden layers which are trying to identify, the grossest features first, and from there it is trying to piece together the grossest features to identify more intricate features. So let me directly go to this slide, which might be, yeah, more instructive. Okay. So I was telling you, right? First, in the first layer, this is kind of a stencil. All these are called the neurons. This is my input layer. This is my output layer. So I had a matrix. My picture is like a matrix, 258 by 258. So I linearize it. Okay. When I say linearize it, I mean I have corresponding to each pixel, I have a neuron over here. Okay. Then in the first layer, I look for edges. See, these are the edges.
Thank you.
Any question?
ते नवीन नव्हतं असल्यामुळे तो मशीन पण गडबडती थोडी. थँक्यू. मैं नेक्स्ट वीक मैं absent मिलता क्योंकि वो क्रेडिट.
Santosh, can you mute yourself?
Yeah, I have muted him. Please continue.
Okay. Yeah. So in the first layer, we look for the edges. In the next layer, we look for loops and lines. See, I connect these edges together to make a loop, which forms this loop of 9. And then I also look for lines. Okay. Then piecing together loops and lines, I look for pattern. This is my pattern over here. Okay. So it's like a stencil. In this layer, the different neurons will have it's like a stencil. Whether your so this input layer is the input layer for this next layer. This layer is the input layer for this next layer, and so on. Okay. And using these stencils, I want to see whether lines are present, whether edges are present. I look for certain edges in this layer. In this layer, for example, I look for loops by combining the edges present in this layer. I also look for lines using some of the neurons. In this layer, I combine the loops and lines to look for different patterns. either 9, 8, 7, or so on. Okay, whatever matches, that is my output. So this is the rough idea. And nowadays, you have ready-made codes. You just have to use that as a black box. It's pretty easy. So what is more important is to understand, is to define a problem which is solvable and also which is important at this point of time. Yeah, so this is the gradient descent method, which stencil. So suppose I am teaching my neural network to identify only 9. Okay. So in 9, I don't have any, what do I say? Some features will not be present, right? So those weightages of those stencils which are not important for identifying the number 9 will be given 0 weightages. But how will it know? To start with, like your least square method algorithm, we'll start with some trial value. Suppose I'm fitting y equal to mx plus c. M and c are my weightages. I will start with some trial value. I'm a machine. I don't know what is slope, what is intercept, right? So I'll start with a trial value, predict a straight line. I'll see if it is matching my this thing properly, data points or not. If it is not matching, according if it is the slope is less or more, I change it. So the exactly same thing happens for all the weights in these various layers. Okay. So, and that method is known as the gradient descent method. Okay. It's very similar to the LM algorithm of least square minimization. Okay. Right. So by trial and error, we have various epochs. Epochs is one epoch. When you encounter the word epoch, it doesn't. It just means one trial, two trials. So by 50 or 60 epochs, you get the best fit set of weights, which will result in a model trained enough to identify, for example, the letter 9. If I feed any other number other than 9, it will say it is not a 9. Okay. Fine. So these are the network performance diagnostics. Okay. Accuracy, training, validation, accuracy. So while you are training, at the end of each epoch, each trial, you match your prediction with the data, right? So that is the training, validation, and accuracy. After your machine, after your model has been trained, after training also there are various metrics to test how effective your model is. Okay. So these are the precision, recall, F1, and these metrics are useful in various. So precision is useful when the cost of false positive is high. For example, spam emails. Suppose I am developing a neural network to detect spam emails, right? Now, it may so happen the neural, I mean, see, at the end of the day, it is a machine. It will not do, 100% right job, right? It is not a program, as I mentioned at the very outset. So 100% correct, it will never be. It's just experience, right? And as you know, if you are guided by your experience, sometimes you might be wrong. Here also same thing happens. So when the cost of a false positive is high, we use this metric to judge whether our neural network is doing fine or not. This is the precision. And then we have recall when we have, the cost, high cost is associated with false negative. Right. So, yeah, so this is our what I maybe will take a few minutes to just, combine these two ideas which we discussed today. I hope I have given you motivation enough to understand why it is important to classify grand designs and flocculants and how it can be done using a convolutional neural net. So as of now, there were only 200 and about 500 flocculant galaxies which were identified in the literature. So we used those as our training images, right? Like you have to give an alphabet book to the kid to get trained, right? Before you ask the kid to identify alphabets in a test, right? So these were our training images, the alphabet books. Okay. And we downloaded the clean images from SDSS. we used this publicly available architecture AlexNet. Okay, these are the details, various layers and all, convolutional layer. Convolution is like a kernel. Okay? And anyways, so these are the details, AlexNet we used. After that, sorry. Yeah, these are the various parameters of the network which we designed. If you are keen to know the details, it is available on archive. Okay, right. So network performance while training. So as you said, see, these are the epochs, various trials. The training loss kind of saturated and the validation accuracy kind of also increased with time, right? So that, that those were the indications that I am going in the right direction. This is very much similar to your chi-square, right? So how do you know you have a best fit when your chi-square value is small enough, right? So since our chi-square, for example, training loss was, getting smaller and smaller, we knew that we were on the right track, and vice versa for accuracy. This is the confusion matrix. This is the metric to test after the training was completed. And so we saw that these are the right predictions for flocculants and right predictions for the grand designs, right? And these were the wrong predictions. The wrong predictions were very small, 0% and 11% respectively. So which says, if you do well in the test, that means you have been trained well, right? Okay, right. And these are the, again, network performance measures after training. But anyway, the confusion matrix has already told us that it has fared pretty enough. Right. And these are the feature maps. See, this is my training image. So this is the grossest form of the training image, It is kind of, making it blurry and blurry and blurry. And this layer actually is identifying the grossest features. This one, then the next one, and so on. Okay. So these are the different features. These are the feature maps, which later the trained model will look for in the new images for finding for new classifications. Yeah, this is for the grand design. Right. So now we had, about 1300 spiral galaxies identified in the Galaxy Zoo Citizen Science Project, which were not classified into flocculent and grand designs. We used our trained model and did the classification, and we actually ended up with 500 flocculents and 700 grand designs. These are new classifications. Okay. And visually also, since the number is not that big, we visually checked also, how bad the classifications were. And this is how bad or good. Actually, it did pretty well. Only 134, 1354 galaxies, the classifications were not good. Right? So this is a subset of the newly classified flocculents and newly classified grand designs. You see, the flocculents look like the flocculents, right? It has not predicted wrongly. And the grand designs look like the grand designs. So the grand designs, if you remember, are the clean, spiral arms and so on, and the flocculents are the patchy ones. And these are the, various statistical properties, which are of, interest, scientific interest to us. Okay, so let us not go into that. This is not what we intend to do. So to summarize, we have introduced what are galactic spiral arms, what are their importance, and what are the various types of galactic spiral arms, and what are the open questions. In the second part, we have introduced what convolutional neural networks are. These are machine learning techniques to classify images. And in the last part, I have shown that we have trained a convolutional neural network to classify grand design and flocculent spiral galaxies. And we have actually used that for new classifications of about 500 flocculents and 700 grand design galaxies. Okay, so with that, I come to the end of the talk and would be happy to take questions. But I think I have already, taken 10 extra minutes. So, yeah, I'm done. Any questions? I think there is one in the chat box. After galactic mergers, will the new galaxy form spiral arm, or will it settle into an elliptical galaxy? And does the merger affect star formation in the previous and the merged galaxy? So if it is a complete merger, it will not form a spiral arm. Okay, but if it is a flyby, there are two things. One is complete merger, it will most, high chances are it will go to an elliptical galaxy, highest chances. But if it is just a flyby interaction, it will induce a spiral arm formation. And does the merger affect star formation in the previous and the merged galaxy? Yeah. Previous galaxy, I don't understand what is previous galaxy, but when merger happens, there will be compression of the gas. So it may help in star formation. As you know, gas compression will leads to star formation. But if there is too much of heating, there would be shock waves, and that can disfavor star formation also. Okay. I hope I have answered your question, Anudeep. Okay, so Anudeep's question was, it was a direct message. After galactic mergers, will the new galaxy form spiral arms, or will it settle into an elliptical galaxy? So it will settle into an elliptical galaxy. This is the answer. And does the merger affect star formation in the previous and the merged galaxy? Yes, the merger will affect star formation in the merged galaxy. It may favor star formation or may not favor star formation, depending on the situation. Yeah. Any other questions? You can either type or unmute yourself and ask directly. How is deep convolutional neural network different from multi-layered perceptron model? Okay, so multi-layered perceptron model, which I intended to discuss, but we didn't have much time, is a fully connected neural network. Okay, that means I showed you various layers, right? Hidden layers, input layer, output layer. There can be, for us, there was about 10 to 15 layers. So each neuron in one layer was connected to all the neurons in the next layer. This is what happens in a multi-layer perceptron. But in a deep convolutional neural network, it is not so. It is not necessarily so, because it makes it humongously complex. And it is not worth also. Okay. So does that, yeah.
Yeah, it does. But then how does one take a decision? How do you decide whether to go for a DCNN or for a multi-layered perceptron model with less number of less number of layers, number one, and less number of neutrons in each layer? I mean, you can always decide how to design your model, right?
Yeah. But I mean, it has to. This is interesting. I mean, we have to check what sort of images you are trying to. I think if it is an image classification problem, which for which we use, I mean, the name convolutional neural network, I mean, is very much related to mainly, image classification. I think for image classification, multi-layer perceptron would be. I think it will not. It will be very difficult to train because the connections are, like exhaustive. Each neuron is connected to all the neurons in the next layer. So that increases the number of weightages and all this, right? So it will be the number of free parameters, or if I say the weightages, will be much higher. So training will be very difficult. So I think it is much better to go for a DCNN when you are going for an image classification.
Okay. So, all right. There is something also something called associative memory, where you store the images, right? You learn and store the images. Is it anywhere connected with this? Or maybe I'm asking totally off the track.
Yeah,
Yeah. Anyway, you can.
Encountered it. I'm sorry about that. Yeah.
Okay. Fine. Thank you.
Any other questions?
Okay, maybe just one more very perhaps a silly question. When you say convolutional neural network, does it have anything to do with the usual mathematical function of convolution?
Yeah.
Is it anywhere related?
Right.
So where is that taking place here in this?
Yeah. So I talked about this stencils, right? Kernel.
Yeah. Yes. Okay.
So I will
Okay, yeah, that is a kind of. I see. Okay.
I will just. So as I said, it looks for various features. The first thing to look for is the edges, right? So
Right.
you can imagine, a stencil where you have edges, right?
Uh,
Right.
okay, okay,
Yeah.
correct. Yeah.
So this stencils would look for edges. This
Mm,
stencil, which is associated with this neuron, it would look for
mm,
loops and lines. Okay, and if this
okay.
stencil actually gets the input, then yeah, the weightage will be high. If not, then we would know that these loops or lines are not important for the uh, image which we are going to classify. So this stencil is nothing but the proxy for this kernel or the
Uh-huh.
convolution function in mathematical terms.
Okay.
So it is yeah, related to that feature extraction or feature
Mm,
detection part.
okay, thank you.
Any other questions?
There are no questions on the Google Sheet or
Okay, let
here
us.
as well.
Google Sheet. Okay, I didn't check the Google Sheet, but there are
Yeah,
no
I
questions.
checked. So there are no questions so far. And so unless there are questions in the chat, I think
No,
then
there are
there
no
are no
questions.
other questions.
Okay. Shall we end the talk then?
Yeah, then we can end the session. Yeah. Thank you very much for giving the interesting talk.
Thank you. Thank you for inviting me. I actually enjoyed giving the talk.